Hey everyone, as you'll be blessed here, making it clear, making it plain, opening up the heavens for my teaching is like spring rain. And today we're going to determine how to get the empirical formula of a compound using the percent composition. Let's go. All right, let's go ahead and get started on how to determine the empirical formula using percent composition, part 1. This is part of the chemical composition series, and so we're just going to cover the basics in this first part. All right. So our objective, we're going to use the percent composition of a compound in order to determine its empirical formula. Pretty straightforward. So how do we break this down? All right, our key concept here is relationships between measurements determine the form. So when we break that down, this means that we're examining the relationship of the law of definite proportions. That means that atoms combined in fixed whole number ratios. So if you haven't seen my previous video on empirical formula, I suggest you check that out. But we are looking at fixed whole number ratios when we're talking about putting together an empirical formula. Next, we have measurements. In order to find the empirical formula, we need to take into account the mass of the atoms that are involved and the number of atoms that are involved, okay? And then finally, the form that we're simply going to focus on today is the empirical formula only, all right? So what is an empirical formula? Here's just a quick review. It is the reduced or simplest form of a chemical compound. We have C6H12O6, which is a molecular formula, and it has a common factor amongst its three subscripts of 6, 12, and 6. So using the common factor or the greatest common factor of 6, we can reduce all of that down to C1H2 and O1, which is CH2O. All right, so CH2O would be an empirical formula, and C6H12O6 would be the molecular formula. So we're going to learn how to actually get that last part, the CH2O, all right? So there are several steps involved, all right? And I tried to organize this as best as I could so that you could easily follow and understand and even set this up on your own if you ever would have to do this on your own, okay? So in order to determine the empirical formula using percent composition, here's what we need to do. We need to organize our percentages and convert them to gram. Basically, we assume that we have 100% of a substance. If we have 100% of a substance, we have 100 grams of a substance, and we can easily just take those percentages and turn them to grams. You'll see that in an example. Then we're going to get the molar mass of each element. Next, we'll find the number of moles by dividing each element by its molar mass. That comes from the periodic table, all right? Then we're going to divide and scale to the nearest whole number as needed. And then we'll finally use those whole numbers to write our empirical formula. So let's get started, shall we? Example number 1, a compound of silver has the following analytical composition: 63.5% silver, 8.25% nitrogen, and 28.25% oxygen. So let's calculate that empirical formula. So the first thing I'm going to do is I'm going to find all my percentages, and I'm going to change them to grams. We assume that if we have 100 grams of a substance, then 63.5% of 100 grams is 63.5 grams for silver. So we do that one element at a time. So we got 63.5 grams of silver, 8.25 grams of nitrogen, and 28.25 grams of oxygen, okay? So next, we go to the periodic table and we find the molar mass for each one of these elements. So silver, I'm going to use a mass of 107.9 grams. Nitrogen, I'm going to use 14 grams. And oxygen, I'm going to use 16 grams, okay? If you have questions about rounding, I try to keep it, to at least 3 sig figs. Okay, if it's incredibly close to a whole number, I just round it up to a whole number, okay? But notice how for silver, I used 107.9, not 108, okay? Just pay attention to that. And if you're not paying attention to that, that will actually slightly adjust your answers or cause your answers to fluctuate, and they might be slightly different from the ones that I provide in this video, okay? Next, we got the percentages organized, and we got the molar mass of each element. So what we're going to do is divide across and find the number of moles, okay? So when we divide across, I'm going to do 63.5 and divide it by 107.9 for silver. I'm going to do 8.25 grams and divide it by 14 grams for nitrogen. And I'm going to do 28.25 grams and divide it by 16 grams for oxygen. This gives me three numbers, 0.59, 0.59 again, and 1.76. All right, so what do I do next? I have these decimals. How do I write a formula when I have all these decimals here? Well, now we have to scale as needed. So we divide it, but now we may need to divide and scale as necessary to try to get a whole number. You must divide or scale by multiplication. There's no other way out of this. So how do we figure that out? Well, just like with C6H12O6, we assume that there was a common denominator of 6. So if we set this up as a formula, Ag.59, N.59, and O 1.76, we can set this up as like a theoretical formula. And we can actually assume that there has to be some type of common factor between all of these. So let's make an assumption that 0.59 is our common factor. If we do that, we're going to divide every one of our subscripts by the same number, by 0.59, okay? Now watch what happens when we assume that the common factor is 0.59, and then we continue to divide that across into each subscript. 0.59 divided by itself is 1, and so that happens twice. But 1.76 divided by 0.59 gives you 2.98. So you have Ag1, N1, and O 2.98. Well, the thing is, 2.98 is so remarkably close to a whole number, like 3, it's okay to round it up to 3. So that means silver, nitrogen, and oxygen in this composition combines with 1 atom of silver, 1 atom of nitrogen, and 3 atoms of oxygen. So the final equation is the final chemical formula, which is the empirical formula, is AgNO3. How do we know it's empirical? Because they have no other common factor other than 1. All right. And so here's the work all over again, just so that you can see it all the way across in the table. All right. Okay, so in our next example, we have a compound containing 34.9% vanadium and 65.1% fluorine, which is used as a catalyst in chemical reactions. So I'm not just making this stuff up, okay? So let's determine its empirical formula. First, let's organize those percentages into grams. So 34.9% becomes 34.9 grams. And 65.1% becomes 65.1 grams for vanadium and fluorine, respectively. Next, let's run to that periodic table and get the molar mass for each element. So vanadium is going to have a mass of 50.9 grams, and fluorine is going to have a mass of 19 grams. What's our next step? Simply divide across. We're going to divide across. So 34.3 grams divided by 50.9 grams will give us 0.69. And for fluorine, 65.1 divided by 19 gives us 3.43. All right, so we have these decimals, but just like before, we're going to assume that one of these numbers is the common factor or plays a key role in finding the common factor so that we can actually get the empirical formula. So let's rewrite this. We got V 0.69 and F 3.43. Okay, so we're going to assume that our lowest number, 0.69, is actually a common factor between these two numbers. So let's do that. We're going to divide, okay, divide and scale. So we're going to divide by 0.69 as the common factor. When we do that, we are going to get 1 for vanadium. And then what are we going to get for fluorine? We're going to get 4.97. 4.97 is so remarkably close to 5 that it is actually safe to round that up to 5. So the empirical formula for this compound containing 34.9% vanadium and 65.1% fluorine is VF5. 1 atom of vanadium, 5 atoms of fluorine. All right, VF5. And here's the work so that you can see it all the way across, okay, from left to right. All right, so I hope you survived the last lesson. Today we're going to determine the empirical formula using percent composition, part 2. And here's the problem. Here's the question you might be asking. I reduced and I still see decimals. So what do? So let's look at an example here. If you haven't seen my previous video on determining percent composition, the basics, you really need to see that first before you move on to this, all right? Because this might have additional steps and make it a little bit more complicated to understand. All right, so get that first, then come back here. But now, diving in to this particular problem, we have an oxide of phosphorus, which is 56.34% phosphorus, and the rest of it is oxygen. So next, we're going to calculate the empirical formula, okay? So we get the percentages and we convert them to grams. So the first step, 56.34% becomes 56.34 grams. But what happened to the rest of the oxygen? Well, there's only 2 elements. If one is 56.34, then the rest must be the difference from 100. So if we do 100 minus 56.34, we're going to get 43.66. Okay, so that's actually the mass of oxygen that we have in this compound. All right, we get the molar mass. Phosphorus is 31 grams. Oxygen is 16 grams. Where do these numbers come from? They come from the periodic table. Make sure you know how to find the mass on the periodic table, okay? Next, we're going to do what? Divide across, okay? So when we do that, it's 56.34 grams divided by 31 grams. And then 43.66 grams divided by 16 grams, okay? So that takes us to 1.82 for phosphorus, 2.73 for oxygen. All right, so this is getting a little interesting here. So if you saw my last video, we had some we had some decimals that were less than 1. This time the decimals are all greater than 1. So how are we going to navigate through this problem? Well, let's go ahead and set it up. So if we were to write this as a theoretical formula, okay, theoretical chemical formula, we got P 1.82 and O 2.73. Well, if we try to use 1.82 as a common factor, like I instructed you to do before, we get P1 and O 1.5, okay? So that's the issue. We still got a decimal. We can't round that. We are only allowed to scale and divide until we get a number that is remarkably close to a whole number. So what do we do with this 1.5? This is where you start scaling, okay? Scaling or multiplying by another factor, okay? So what can I do with this? I can actually look at 1.5 and rewrite that as a improper fraction of 3/2, okay? So the thing is, how do I get rid of this fraction? How do I take this decimal or this fraction and turn it into a whole number simply by using multiplication or division? I can actually multiply this number by 2. So if you take a decimal of 0.5 or a fraction of 1/2, and you can multiply everything by 2. By multiplying it by 2, we get rid of the 2 in the denominator, and so we're left with 3. So 3/2 times 2 gives me 3. We have to scale everything by 2 because the phosphorus is attached to the oxygen. So we multiply phosphorus by 2 and oxygen by 2. So 1 times 2 is 2, and 1.5 times 2 is 3. All right, so the final formula that we get is P2O3. Here's the work again so that you can see it. And I'm actually going to show you another way to get these empirical formulas if you have the number sense, or if you've developed enough number sense to identify some patterns. If we look at this, we have 1.8 and 2.7. Now, if you're familiar with some of your times tables, those number patterns look familiar. They look like 18 and 27. So if we rewrite this, I can say this is P18 and O27. Well, I know if I look at 18 and 27, they definitely have a common factor of 9. All right. So by dividing both of these numbers by 9, I can go directly from 18 to 2 and 27 to 9. Or if you're really good with your number sense, you can actually see that the common factor would be 0.9. Okay. So 1.82 divided by 0.9 and 2.73 divided by 0.9 would give you numbers that are close to 2 and 3. So by identifying number patterns, you can actually also do the reduction or simplify these ratios very easily, okay? But that only works if you can identify number patterns. If you're still struggling with that, then I highly suggest you still do it the algebraic way and divide each term out and then scale it back up, okay? So let's try one more example. Cubic zirconium is 83% zirconium and 17% nitrogen. Determine the empirical formula for this compound. Okay, so let's go ahead and put those numbers in. We got 83% and 17%, so that takes us to 83 grams and 17 grams. Next, we go to that periodic table, that faithful periodic table, and we find the molar mass of zirconium and nitrogen. Those numbers shall be 91.2 grams and 14 grams. Okay. What's our next step? We are going to divide across 83 divided by 91.2 and 17 divided by 14. This gives us 0.91 and 1.21. Okay. Excellent, excellent, excellent. I'm glad you know how to use a calculator. So let's keep it moving. We got 0.91 and 1.21. So let's write our theoretical chemical formula. 0.91. So ZR 0.91 and N 1.21. Okay. If we assume that 0.91 is a common factor, we're going to divide each number by 0.91 and we get 1 and 1.33. Okay. So hold up. Last time we had a half. This time we got 1.33 or 0.33 in our decimal. Well, if I was to try to put that into a improper fraction, that reminds me of 4/3. 4/3. 4 divided by 3 would give me 1.33333. You know, the repeating decimal patterns that they teach you in math class? Yeah, that thing. Okay. So the thing is, how do we get rid of a third? Well, the same way we got rid of a half by multiplying by 2, we can get rid of a third by multiplying by 3. So if we multiply everything by 3, we can get rid of that third. So 1 on the phosphorus times 3 will give me 3. And 1.33 times 3 will give me 4. So we get Zr3N4 as the empirical formula for cubic zirconium. Again, here's what all right, so again, what if you could do this without doing all that math? Well, you're still doing some math, mental math. You can use, again, number patterns to identify what a common factor could be. So if we look at 0.91 and 1.2, you can recognize that these are all multiples of some form of 3. So if you leave it as 0.91 and 1.2, then you got to recognize that the common factor that takes them to a whole number is 0.3. 0.9 divided by 0.3 gives me 3. 1.2 divided by 0.3 gives me 4. The other thing you can do is just scale it up a little bit and you get P9O12. With P9O12, you recognize that 9 and 12 have factors of 3. They are multiples of 3, okay? And so if you divide them by 3, you get Zr3N4 again. So you still end up dividing and scaling, all right? But it depends on how your brain works. If you can identify patterns, then you can begin to find the simplest form or the empirical formula this way. But if you're not good with number patterns, then you really need to stick with dividing by the lowest, dividing by the smallest term. I like to do the smallest term. And then scaling up as you need to, okay? You're assuming that the common factor is there. Thank you for tuning in to You'll Be Blessed Education. I really hope you were truly refreshed by this teaching. And if you were, there are several things you can do. First, you can click the like button below. Second, you can leave a comment below describing how you were blessed by this video. Third, share this video with anybody you know that will be blessed by this teaching. Again, thank you for tuning in to You'll Be Blessed Education. This is You'll Be Blessed. Be blessed. I'm out.